For this problem, we were given two values, each of which were a part of the same special right triangle. So for this, I chose a 30, 60, 90 special right triangle. So I chose 16 and 16 root 3. And then we were given this point in rectangular form. So this would so it'd be representative of this point right here. But I turned it into like components. So 16 and negative 16 root 3. And because this is a special right triangle, we know that this angle, which corresponds to the x root 3 value, has to be 60. But in this case, because this triangle would be in the fourth quadrant, it has to be negative 60. And that because the 2x value, so that's 2 times whatever this value is, which is 16, which is makes this 32. Then we had to change this into polar coordinates. So for that, you need the hypotenuse of this triangle, or which is technically the radius on a polar graph, and the direction of this. If you think about it like a vector, it's technically the direction, but it's the angle right here, which is negative 60. Or theta for like the general form, which we'll see here. So then we were asked to find a equation for a polar graph that includes this point in it. So that for this, I chose a limacon graph because, I don't know, I just think it's the prettiest and I think it's cool. So I chose this value to create the limacon. This is 5, and that makes it that number just being there, I just chose it randomly, just makes it so that it has this bubble right here and makes it a limacon. So with that, we know we have this general form, r equals 5 minus a sine theta. And so to find the equation of a graph that includes this point that we found up here, we have to substitute these in for r for 32 and negative 60 for theta, and solve for this coefficient a, because that's like the main point of like what we need. It's not given to us. So to do this, we just plug everything in and solve for a, which I found to be exactly 54 root 3 over 3, or about 31.18, which I just wrote here because it's easier to write than that in my opinion. But so then we pop out this cute little graph, has a little butt right here, and it's lies mostly beneath the x-axis. And we're gonna analyze this. So I found first that these are x-intercepts, this negative 5 and 5, and they have a distance of 10 between them. This point, where it starts to do the loop-de-loop, it's always 0, 0 on a polar graph. It's just at the origin point always, I believe, and that's true for limacons as well. And so from that, I found that negative 26.18, 90, I found that graph, that point, by plugging in 90 degrees for theta, which is just sine of 90 is 1. So it'd be 5 minus 31.18, which is turns out to be about negative 26.18. And because 90 on the unit circle is up here, it'd technically be like going backwards, so it'd be negative 26, and that's why it lies down here, and that's why the loop-de-loop is where it is. The same thing kind of applies for 270. 270 would make this positive because because sine of 270 is negative 1, so it'd be 5 plus 31.18. So that creates the problem of, okay, what happened? So what happened is, because 270 goes this way traditionally on the unit circle, that means you're going positively in this 270 direction. And that's why it appears negative on the graph, but it's technically still positive because you're going in the direction where the 270 is. And that's why this is where it is. And the distance between these two is 10, which is just double this number, which is always fun. And the total distance from this origin point right here and the very bottom of the limacon, that kind of like maximum, like the farthest away it gets from over here, is negative 36.18 distance, or really just 36.18 because distance is always positive. And then the last part of this would be the symmetry, and I found that the symmetry was vertical because you can't see it, but there's a y-axis that runs straight up and down. It's centered on the y-axis, and if you cut this limacon in half and flipped it on itself, it would match up perfectly. So that proves that it is vertically symmetrical.